right, guys. So what we're doing today in most of this chapter 6 is going to be dealing with matrices and revolving around matrices. Now, the first thing we're going to talk about is writing and interpreting augmented matrix and writing an augmented matrix. So for the first one here, we're going to write this as an augmented matrix. Now, to do that, we need the x and y on the same side and the constant terms on the other. So we can write this out to the side. So our first equation, 2x is equal to 5y plus 5. So for this one here, we need the x and y on the same side. And to get that, we're going to subtract 5y from both sides, telling us that we have 2x minus 5y is equal to 5. So we have that one there. That one is set up in the way that we need it. We need to do the same thing to the other equation. We have 3 times x plus y is equal to 17 plus y. So we need to get it in a similar form, x, y. And to do that, the first thing we're going to do is multiply through by the 3. 3 times x can be 3x. 3 times y is going to be 3y is equal to 17 plus y. Now at this point here, we're going to subtract y from both sides, giving us 3x plus 2y is equal to 17. Now that we have both equations with x and y on the same side and in the same order, we can write the augmented matrix. And when we write an augmented matrix, we're just taking the coefficients of each equation. So for the first one here, we'll have 2 from x, negative 5, 5. And with the other equation, we'll have 3 from x, 2 from y, and then 17. And this would be the augmented matrix. Now, sometimes we do draw a line to signify where the equal sign is. X, y, z are variables on the left, are constant terms on the right. And that's it. And it's really standard notation that x is in our first column, y is in the second, and then constant term is last. If we have 4, like the next one here, it's understood that the first one's x, the second one's y, third one's z, and then the last one is our constant, are just numbers. Any questions on A so far? Now, if we look at B, write a system of linear equations represented by the augmented matrix. So we'll have 3 equations. Now, the first one is telling us that 1 times x plus 0 times y plus 0 times z is equal to 6. So really, our 0y and 0z are gone, and it's just really telling us that x is 6. And that's for the first one. Our second one is telling us 0 times x plus 1 times y plus 0 times z is negative 10. Or really, this is just saying y is equal to 10. And lastly, we have 0 times x plus 0 times y plus 1, not 0, plus 1 times z is equal to 4, which is just telling us z is 4. It is negative 10, thank you. So y is negative 10, x is 6, and z is 4. And that is it with this here. Any questions on any of this here? Now, with systems of equations, representing systems of equations by an augmented matrix, we want to get it in one of 2 forms. Either this form, which is reduced row epsilon form, and reduced row epsilon form really tells us what x, y, and z are. We want this diagonal of 1s. Now, row epsilon form is similar, but the numbers in these 3 spots here might not always be 0. We do get the diagonal of 1s, but we don't get the rest zeros. But we're still able to find the solutions. Any questions on this here so far? Now, row operations. Because for the most part, when we solve systems of equations with matrices in Algebra 2, we use the graphing calculator to get that reduced row epsilon form, RREF. But if we did it without a calculator, we would use these row operations. And any of these work with any matrices. And the first one is to interchange two rows. So what we're saying here is we're switching rows 1 and row 2. So we can flip it. We just flip row 1 and row 2. We change the order of them. The second one, we can multiply a row by a non-constant 0. So here, from here to here, we multiplied row 1 by 3. So we multiplied all the terms by 3. Or we can add rows and do the multiplication. So we multiply row 1 by 3 and then add it to row 2. So here we have negative 3 plus 3. And negative 3 plus 3 is 0. 6 plus negative 5 is 1. 15 plus negative 13 is 2. Now when we do this here, we're just affecting row 2. We're not actually doing anything to row 1 in this third example, so it stays the same. Now if you notice this here, by doing 3 times row 1 and adding it to row 2 is now 0, 1, 2. We've changed it. Now it's telling us that y is 2. And we can use it to solve from there. Because the main goal is to get this diagonal of 1s. We're using this to get the diagonal of 1s. And we could go from there to finish solving it out if we want to get it in to reduce row epsilon form, which in this case would look like this here. Now this would be 2. It ends up being 1 if we worked it out. And we use these row operations to get there. Any questions on this so far? So the first thing we're going to do before we really get into this with matrices themselves is perform some of these operations. Perform some of these elementary row operations. Now for A, we're switching rows 1 and row 2. They're going to change places. So for us, all the numbers in row 1 are now going to be in row 2 and vice versa. So row 2, 1, 4, negative 1, 9 is now in the top row. The second row is all the numbers from row 1. 4, 3, 0, 5. Since we didn't do anything to the third row, it stays the same. Any questions on A? B, we're going to multiply row 1 by 1/4 and apply it to row 1. So the first row, every number in this is going to be multiplied by 1/4. Well, 1/4 times 4 is 1. 1/4 times 3 is 3/4. 1/4 times 0 is 0. And lastly, 1/4 times 5 is 5/4. Now the other rows we didn't do anything to, or other rows we didn't do anything to, so they're going to stay the same. Any questions on this here? Any questions over anything we've done so far? Now the last one, we're going to multiply row 2 by -2 and then add it to row 3. And the row this is really affecting is the third row. So what that tells us is in this matrix, we're not doing anything to row 1. So it's still the same. Row 2 is not being affected. The only one that is changing is row 3. Row 3 is the only one that's going to have a change. Now we can do some of this here off to the side. The first thing we'll need to do is multiply row 2 by -2. And on a lot of these here, I do have scratch work. I work some of this out to the side so I see how it looks. So multiplying row 2 by -2, our row 2. So off to the side, we'll say 2 times 1 is -2. 4 times -2 is -8. -2 times -1 is 2, our line, and 2 times 9 is -18. And we're adding this to row 3. Well, row 3 is our 2, 0, -3, -8. And we're adding these together. Well, -2 plus 2 is 0. -8 plus 0 is -8. 2 plus -3 is -1. -18 plus -8 is -26. Questions on any of this here? Any questions on anything we've done so far? Do we kind of understand how these row operations work? And the main goal in using all these here is to get a highlighter. This here to be a diagonal of 1s. We want those to be diagonally all 1. So that's sometimes why we do a multiplication of 1/4, or we switch to the rows so that we get this diagonal of 1s and then we can solve from here. Row echelon form, echelon, and reduced row echelon form. A matrix in row echelon form, if it satisfies the following condition, any row consisting entirely of zeros are at the bottom of the matrix. If we have all zeros, they're at the bottom. For all other rows, the first non-zero entry is 1. This is called the leading 1. The leading 1 in each non-zero row is to the right of the leading 1 in the row immediately above. So what that's saying, because I believe 1, 2 made sense, we get that. 3, all that's saying is if we have a matrix, we have 1, 2, 3, bar 4. In the first row, this here is the leading 1. The next row, each non-zero, the leading 1 in each non-zero row is to the right of the leading 1 and immediately above it. So what that means is that the first number in the next row needs to be 0, and we have 1 to the right of it. If we had another row, its 1 needs to be 1 to the right of the previous one. We need this diagonal of 1s. We can't have two leading 1s over the top of each other for it to be in row epsilon form. Note a matrix is in reduced row epsilon form if it's row epsilon form with the added condition that each row with a leading 1 entry has zeros above the leading 1s before it. Essentially everything else, all these others are 0. We only have the leading 1s. We don't have anything else on that side of the bar. Now, solving a system of linear equations using Gaussian elimination, write an augmented matrix for the system. Use elementary row operations to write the augmented matrix in row epsilon form. Use back substitution to solve the resulting system. So the first thing we're going to do is get this into row epsilon form. So we're going to take the numbers in front. So 3, 7, negative 15, bar, negative 12. Our second one is going to be 1, 2, negative 4, negative 3. And the last one, negative 4, negative 6, 15, 16. Highlight it for now. Now the main goal is to get the numbers in these three positions to be 1s. That's the main goal. That's what we're trying to get. Well, if we look at this here, I do notice that the second row's first number is indeed a 1. Yes. So what we can do is take row 1 and switch it with row 2, which tells us that we have 1, 2, negative 4, negative 3. And the second row is now 3, 2, negative 4, negative 3. And the last row stay the exact same. Questions on this here? Now, having the first row have a 1 is going to be helpful because we need the two numbers underneath it to be 0. So we need this 3 and this negative 4 to be 0. So what would I need to multiply 1 by to get the 3 to cancel? Negative 3. So what we're going to do now is multiply row 1 by negative 3 and add it to row 2 to take row 2's place. Thank you. It should be 7, negative 15. And this should be negative 12. Thank you. That was about to throw everything off. For some reason, I just put the other two numbers back there. Didn't mean to do that. Yes, okay, everything else is in the right order. So what we're going to do now is we're going to multiply row 1 by negative 3 and then add it to row 2. Now we can do this off to the side as scratch work. So if I multiply row 1 by negative 3, we'd have negative 3, negative 6, 12, and then we would have 9. Because we multiply each of the numbers in row 1 by negative 3. So negative 3, negative 6, 12, 9. And we're going to add it to row 2. Now row 2 is our 3, 7, negative 15, and negative 12. And we're going to add these together. Well, 3 plus negative 3 is 0 like we wanted. Negative 6 plus 7 is 1. That's kind of nice. 12 plus negative 15 is negative 3. And 9 plus negative 12 is negative 3. So we know for certain we're not going to do anything to row 1 from here on out. Because we need it as a diagonal of 1. It's got the 1. Yes? Negative 3. Our second row, the one we just changed, is now 0, 1, negative 3, negative 3. Any questions on anything we've done so far? And I haven't wrote row 3 in here specifically just yet, so we'll hold on for it. Any questions on what we've done so far? Well, we also need this negative 4 to be 0, yes? Because we can do more than one of these at a time. But what would we need to multiply our 1 in the first row by to get this to be 0? 4. And the reason I'm using the 1 is because it's easier to make into the other two numbers. So what we can also do is multiply row 1 by 4, add it to row 3, and it's going to take the place of row 3. So we multiply row 1 by 4. Well, we'll have 4, 8, negative 16, and negative 12. 4, 8, negative 16, negative 12. Now row 4 is negative 4, or not row 4, row 3 is negative 4, negative 6, 15, and then 16. And again, we're adding these together. Negative 4 plus 4 is 0, just like we wanted. 8 plus negative 6 is 2. Negative 16 plus 15 is negative 1. And lastly, negative 12 plus 16 is 4. Any questions on how we got to this point here? So, looking at this here, get the highlighter back out. Again, our main goal is to get this here to be a diagonal of 1s, and everything below that line is 0. We almost have that, yes? Because the only thing that we have left that's not 0 is this 2. Well, to get it to be 0, we're not going to use row 1 anymore for this here. Because if I use row 1 in any way, we're going to be adding or subtracting a 1, or a number times that 1, from this first spot. So I can't use it. So what row are we going to have to use? We're going to have to use row 2. Because no matter what I multiply row 2 by and add it to row 3, that first spot is 0. Which is going to help because it's not going to add anything to our first spot. It's only going to affect the second and third spots. So what would I need to multiply row 2 by and add it to row 3, because it's going to affect row 3, to get this middle number to become 0? We need to multiply it by negative 2. Because if we multiply that first row, or not row, second row by negative 2, well, negative 2 times 0 is indeed 0. 1 times negative 2 is negative 2. And negative 2 times negative 3 is 6. And negative 3 times negative 2 is still 6. And then we're going to have row 3. And again, we're going to add these together. Now 0 plus 0 is still 0. Negative 2 plus 2, these cancel out, giving us the 0 that we wanted. And lastly, 6 plus negative 1 is 5. And lastly, 6 plus 4 is 10. Now for our matrix, the first row. Did not change. The second row didn't change. But the third row, that color, is now 0. Okay. Thank you. Is now 0, 0, 5, negative 10. Sorry. 10. I don't know why I wanted to add that negative, but 10. Any questions on how we got to this here? So what's the only thing that's not in its proper place? The 5, yes? So the last thing we can do is multiply row 3 by what? What would I need to multiply row 3 by? What times 5 is 1? Huh? Well, what would we normally do to turn 5 into 1? We wouldn't multiply, we would divide by 5, yes? Well, we can't divide, so the best thing to it is a fraction. We multiply by 1/5, because 1/5 times 5 is indeed 1. So we multiply, well, first row didn't change. We didn't do anything to it. The second row, we didn't do anything to it. But the third row, we multiplied by 1/5. And 1/5 times 5 is indeed 1. And 1/5 of 10 is 2. Now this here is indeed in row epsilon form. Now if we wanted in reduced row epsilon form, we would continue using these similar operations, but what we would end up doing is making these 3 numbers here all be 0. So to make the second row's negative 3 be 0, well, I'd multiply row 3 by 3 and add it to row 2, which would give us a 0. Then I could do the same thing with row 1. I can multiply row 3 by 4, add it to row 1 to get the negative 4 to be 0. After doing that, then I can take row 2, multiply by negative 2, add it to the first one to get it to be 0. We can keep manipulating it to get there. But any questions on how we got to this point here? Now what this tells us is something in particular, because we can plug the variables back in, because we have x, y, z, and then our constant. So the first row is telling me that I have x plus 2y minus 4z is equal to negative 3. The second row is telling me that we don't have anything for x, but I have y minus 3z is equal to negative 3. In the last row, bless you, is telling me that z is 2. Now we're going to work our way from right to left as how I listed them. So what we can do is plug z into the middle one, which tells us we have y minus 3 times 2 is equal to negative 3. Or y minus 6 is equal to negative 3. Add 6 to both sides, telling us y is equal to 3. Well, now we can plug the 2 into z here, and we can also plug in the y value of 3, which tells us that x plus 2 times 3 minus 4 times 2 is equal to -3. Well, 2 times 3 is 6. -4 times 2 is -8. Or that we have x minus 2 is equal to -3. Add 2 to both sides, telling us x is equal to -1. So our solution is -1, 3, 2. Questions on this here? Any questions on anything we've done so far? So we see how this works. Now, on a whole, what we just did, each individual step wasn't anything crazy hard. But there was a lot of steps to do, and knowing the right order to do them is sometimes challenging. Now, I'm going to show you this here. In the calculator, we can go second matrix, second x to the -1. We can go over to edit. And input, so here we have 3 by 4, our augmented matrix, what we started with. So 3, 7, -15, -12. 1, 2, -4, -3, -4, -6, 15, 16. We input this here. Now, once we finish inputting it, we could say second quit. Second matrix, over to math. Now, in this list, all the way down towards the bottom, we have 2 options here at A and B. A is REF, reduced epsilon form. B is reduced row epsilon form. Or sorry, A is row epsilon form, B is reduced row epsilon form. And what we got in the end was row epsilon form. And I can go second matrix A, enter, and we get this here. Now it is a little bit different than what we had. For some reason it's doing fractions, but that's fine. But if we look at what we had for our REF, second matrix A, because we did know the answer was -132, yes? So from top to bottom, in reduced row epsilon form, the third set, or the last set of numbers should be -132. And that's the solution we found. Now, our REF, or not REF can be a little different because we switched rows 2 and 1 and made it into a nicer form. So if I went back and switched those 2, like we did at the start, and said 1, 2, -4, -3, and then put 3, 7, -15, -12, and quit, and did our REF, well, we end up getting the same thing, but that's fine. Because in either case, we ended up with a little bit nicer numbers. Any questions on this here? Now, as daunting as this may seem, this here, these steps are actually what you're going to be doing on the assignment. It's giving it to you from one to the next. So we're filling some of the stuff in. So if we look at the first one, step 1, all the way down to the end. So here, it ended up getting into reduced row echelon form. And we're going through and saying what we did from step 1 forward. So if we look at this here, row 1 or row 2, well, it's telling us row 1 changed, yes? Well, the first number was 4, it's now 1. The second row was negative 16, it's now negative 4. The last one was negative 4, it is now negative 1. So what does it look like we did? We multiplied everything by 1/4. So that'd be the first part of your answer. Step 2, we multiplied something by row 1 and then added it to row 2, replacing row 2. So what would we need to multiply 1 by when added to negative 4 to give us 0? So we multiply it by 4, yes, because 4 times 1 would be 4. And if we add it to negative 4, we get 0. If we did 4 times negative 4, we'd get this. 4 times negative 4 is negative 16. And negative 16 plus 21 would indeed be 5. And 4 times negative 1 is negative 4. Plus negative 11 would indeed be negative 15. Step 3. Well, the first row is still the same, but the second row, 0, 5, negative 15, is now 0, 1, negative 3. We multiplied row 2 by 1/5. And lastly, we multiplied row 2 by something and added it to row 1, applied it to row 1, so that 1 stayed the same, but negative 4 became 0, yes? So what would we multiply row 2 by? We multiply it by 4. Now, did row 2 change at all for this one here? Well, no. So the row 2's last number should still be the same. It should still be negative 3. Now, to do this, we multiplied row 2 by 4. So row 2, we can say off to the side, is 0, 4, negative 12. And we added it to row 1. 1, negative 4, negative 1. Well, 0 plus 1 is 1. We have that. 4 plus negative 4 is now 0. And negative 12 plus negative 1 is negative 1. So the solution is telling us x is equal to negative 13 and y is equal to negative 3. Questions on this here? Now, if we wanted to make sure and check our answer, we could plug this into the calculator and do RREF and see if we do indeed get 1, 0, negative 13, 0, 1, negative 3. If we do, we ended up in the right spot. Questions on this here? Let's look at one last one. This here is the last thing we're going to look at. Well, we'll have to look at it probably on Monday because we're running out of time. But what do we think of this here? On a whole, not too bad, very tedious. Would y'all agree? And the one downside to this is if it turns out that this is no solution or not invertible, as we say, doesn't have an inverse, doesn't work, there are sometimes there's no way to get there.